All right. The first problem is allowing us to find the value of a sum and then also check it on the calculator. You won't have to use summation on your calculator for the AP exam, but it's kind of nice to know how it works. So, first of all, using the properties of summation and theorem 4.2. So, this is on the front of our notes. We had, let me see if I can find this. We had, these little rules here. So, this first one is just there's a constant, ours is negative 18. The summation rule is that because you're going to be adding negative 18 a certain number of times, it's n times that value. So, oh, so there we go. So this is going to be 30 is n times negative 18. 30 times, 3 times 18 is 54. So this is going to be negative 540. And I have some screenshots over here, but I can show you where this is on the calculator. So just make this a little smaller. So, okay. If you go into math and you scroll down a bit toward the bottom, option 0 is summation. And you can type in, now we're not going to put in I, we're going to put in x equals 1. And we're going up to 30. And the expression is just negative 18. And this confirms our result for us. Okay. Again, you don't have to use the calculator like that for the AP test, but it's just kind of nice to know what that's talking about. Our chapter 9 deals with summations, more of these summations. So this is just sort of like an intro to it. All right, now this answer key is going to take a little while to get through because all of these questions have lower sums and upper sums, and so I'm just going to kind of methodically write all of this out. So bound the area of the shaded region by approximating the upper and lower sums, use rectangle of width 1. It's kind of hard to see, but there's this like pink shaded area here. So they want us to use rectangles of width 1. And then when you're doing your upper and your lower sums, I'm going to start with the lower. So the lower sum would be I want the rectangles to be underneath the function. So, so how do I accomplish that? I need to do a left sum because this function is increasing, and so using the left endpoint of the rectangle is going to keep everything underneath. So marking it off on the picture really helps. So we're going to estimate the integral from 0 to 4 of whatever this f of x dx is. We're estimating it to be the width of each rectangle, which is 1, times, I like to just put the function values to start, f of 0 plus f of 1 plus f of 2 plus f of 3. And then we just use the graph to estimate those values. So f of 0 looks to be 1. F of 1 looks like it's 3. F of 2 is 4. And f of 3 we kind of have to estimate. I'm just going to call it 4.5. So this is 4 plus 4 is 8. 8 plus 4 is 12.5. So that's our this is our lower, which in this case is a left sum. And remember, lower and left don't always have to go together. So it depends on whether the function is increasing or decreasing. So that's why the picture is important. So this is the lower, and then we're going to find the upper. So the upper, you're still using these same rectangle widths of 1. So I'm still drawing these in. The upper means we want every rectangle now to be on the right, because using a right endpoint, because that will overestimate the area. That's why it's called an upper sum. So now we're getting this area. We know it's going to be too large because it contains the area we want plus a little extra on the outside. So this upper, which in this case is the right, will give me an estimate for the integral from 0 to 4 of f of x dx. The rectangle width is still 1, but now our endpoints start at 1. So f of 1 plus f of 2 plus f of 3 plus f of 4. Okay, and then these values, that's 1 times f of 1 was 3, f of 2 is 4, f of 3 we said was about 4.5. And f of 4 looks like it's right at 5. So our upper sum is 7 plus 9.5, so that's 16.5. Again, that's just our estimate here. So it says use those to bound the actual area. So that just means all we know right now is that the actual area is somewhere between 12.5 and 16.5. So I like to write that like this. The actual area is the integral from 0 to 4 of f of x dx, and it sits between 12.5 and 16.5. All right, for number 34, same thing. The shaded region, it's hard to see. It's between 1 and 5. So we're still using rectangles of width 1. Now this is a little different because f is increasing for a bit and then decreasing. So whether we're using a left and a right kind of depends. We're trying to find a lower sum. So I'm going to draw in the rectangles first. So here I'm using a left sum. So between 1 and 2, I'm using a left endpoint. But then everywhere else, I'm going to connect to the right because now the function is decreasing, and that I want this to be an underestimate. Okay, so we're doing this. And then there is no rectangle here. That is what I would have to do for the right. So from between 2 and 5, I'm using right. So that means that our estimate for the integral from 1 to 5 of f of x dx, all of the rectangles have width 1. And then I'm going to show my function values. So the first one's at f of 1. The next one is at f of 3. And then f of 4. And technically there is an f of 5 in there. So this should say equals, about equal to. So f of 1 is 4. F of 3 is also 4. F of 4 is 2. And f of 5 is 0. So our lower sum is 10. And then the upper, we're going to do kind of the same idea, but starting out here, I want to use this rectangle here for the first one. So I'm using for the upper on 1 to 2. Now I'm going to switch to a right endpoint. And then from 2 to 5, I'm going to switch to a left, because if we look at that, if every rectangle has its left corner on the function, then all of those rectangles will be outside of the shaded area. All right, so that means that the integral from 1 to 5 of f of x dx is about equal to width of 1 times f of 2. That's the height of the first rectangle. There's another f of 2, the height of the second rectangle. And then it's f of 3. And then it's f of 4. And so that's 5 plus 5 plus 3 plus 4. That's 17. So this time we know that the actual area is somewhere between 10 and 17. So I'm going to write that like this. And that's my final answer. Okay, more of the same for this one. So start with my lower. Now what's the lower going to be here? This time the lower is a right sum, because to stay underneath this decreasing function, you're going to have to connect to the right side. And we're really going to use some estimating here because we don't know what f's function actually is. So the integral from, we're going from 0 out to 5, it looks like, of f of x dx is about equal to the width of every rectangle, which is 1, times f of 1 plus f of 2 plus f of 3 plus f of 4 plus f of 5. You can also double check. It's easy to miscount here, but I have 1, 2, 3, 4, 5 rectangles and 1, 2, 3, 4, 5 function values there. All right, so this is 2 plus 1. And then let's estimate the rest of these. So I think I said this next one. I think I did like 1/2, 1/4, and 1/8. You could have something slightly different there. That's okay. You might say this is more like 3/4, 1/2, whatever. And then, so this is 3. Actually, you know what? I think I did this both by hand and with a calculator. So just to speed things up for the video. And because these problems are normally calculator problems, 3.875. I also, when we're bounding areas, it's kind of nice to see the decimal version to really see if you are falling between values or not, or if you made a mistake somewhere. So the upper sum will be the left because this is a decreasing function. Sometimes we get that question, how do we know whether or not, without graphing it, how do we know whether this is going to be an overestimate or an underestimate if they just tell us left versus right? If it's a decreasing function, then it doesn't matter how it decreases. If it's always decreasing, the left will be upper and the right will be the lower. So from 0 to 5 of f of x dx, that's going to be 1 times, so this time it's f of 0 plus f of 1 plus f of 2 plus f of 3 plus f of 4. And that is 5 plus 2 plus 1. I'm going to stick with my values, plus 1/2 plus 1/4. And okay, this one at 8 3/4 is going to be 8.75. So we know that the actual area falls somewhere between 3.875 and 8.75. So that is our bounded area for that. All right, getting into some of this practice with limit notation here with the summation formulas. I don't remember having to memorize a ton about the summation rules, but this is good to know. We have limits at infinity, so this is kind of good practice at that. So what this is asking us to do is find the limit as n approaches infinity of this expression. Now, I want to point out this expression multiplies out to be 128 n to the 1, 2, 3, n to the third, plus some other terms on top. The bottom, there's a 6n to the third, plus, or no, there are no other terms down there. It doesn't matter what the other terms are. Remember, when we're taking limits at infinity, we're thinking about what is the horizontal asymptote if I were to graph this thing. And because we have a tie, same exponent top and bottom, it divides out to 128 over 6. Reduced, if I reduce by 2, that's 64 over 3. Okay, for the next one, same idea. The limit, remember to write your limit notation. As n approaches infinity, so what would this be? This would be n squared, I guess I can distribute that, n squared plus n over 2n squared. So informally, again, this is a tie, same degree top and bottom, so that's going to have a horizontal asymptote at 1/2. For number 41, use the upper and lower sums to approximate the area of the region using the given number of subintervals. So there are 1, 2, 3, 4 subintervals here. So the first thing is to calculate your delta x. So it's the end of the interval minus the start divided by the number of subintervals, which is 4. So every rectangle has a width of 1/4. And I like to write that in 1/4, 1/2, 3/4. All right, so let's start with our lower. This is an increasing function, so you can see that the lower is the left endpoint here. So lower is going to be left. The integral from 0 to 1 of the square root of x dx is about equal to delta x, 1/4, times f of 0 plus, I guess it's not f, is it? It's y. Y of 0 plus y of 1/4 plus y of 1/2 plus y of 3/4. I, again, am going to use a calculator for this. Now, you can type everything in. It's square root of things. But also, remember, we did this a lot in pre-calc last year. Type in your function, even if it's just something silly like square root of x. And then you can evaluate this on your calculator screen. I don't know if this is more beneficial for like more complicated functions, but even so, I can say, okay, 0.25 plus, now I'm not going to type in y of 0 because square root of 0 is 0. But otherwise, it's like what we're doing here is saying square root of 0 plus square root of 1/4 plus square root of 1/2 plus square root of 3/4. That's not hard to type in, but I can also remember alpha trace and say y1 of, I'll just start at 1/4, y1 of 1/4 plus y1 of 1/2 plus y1 of 3/4. And that gets me to the answer too. So it's not necessarily less typing, but especially if the function is more complicated, this is a nice option to have. So to 3 places, this is 0.518. And then for setting up the upper, so the upper will be the right sum. You can see that out here. Not going to shade it in, but so what are those function values? Well, first of all, we're using this still to approximate this integral. The width of every rectangle is 1/4. Instead of starting at y of 0, you start at y of 1/4 plus y of 1/2 plus y of 3/4 plus y of 1. All right, and I can either calculate this by hand. For your AP free response, I believe you can just show one or the other. I don't think you need both of those lines. You do need to show what you're doing. You can't just write is about equal to the answer without any work. So you have to show one of these two steps. So I'm just showing both. And then here's a nice thing too about this. I can also go back here and just edit. So I didn't include y of 0 because it was 0. But now I can say, okay, plus y of 1 and add that extra value in. And yeah, I get 0.768. So I didn't have to retype it all. And I can just get my bounds that way. So then this is saying that 0.518 is less than the actual integral from 0 to 1 of radical x dx, which is less than 0.768. Okay, 43. 1 over x. First thing we need to do is get our delta x. There are 1, 2, 3, 4, 5 subintervals. So to calculate delta x, it's the end of the interval minus the beginning divided by the 5 subintervals in this case, so 1/5. All right, so labeling between here, okay, what is this? 1 is 5/5. This is 6 over 5, 7 over 5, 8, oops, I've marked these off, 8 over 5, and 9 over 5. All right, so the lower will be the one on the right. So the integral from 1 to 2 of 1 over x dx can be approximated by a width of 1/5. And then we're starting on the right, so that's going to be f of 6/5 plus f of 7/5 plus f of 8/5 plus f of 9/5 plus f of 2. Or if I want to make this a little easier to type in, I could, I don't know if it's going to be easier or not, but I can do the y1 thing. Or I can just retype this. So it's 1 over 6/5, so that's just going to be 5/6 plus 5 over 7 plus 5/8 plus 5/9, and the reciprocal of 2 is plus 1/2. I think I'm just going to type in the fraction version of this now. Okay, so 1/5 times the quantity 5 over 6 plus 5 over 7 plus 5 over 8 plus 5 over 9 plus 1 over 2. And I get 0.646. Okay, and then for my upper limit, this is a decreasing function, so the upper will be the left. And so the integral from 1 to 2 of 1 over x dx will still be 1/5, but now it will start on the left. So it will start at f of 1 plus f of 6 over 5 plus f of 7 over 5 plus f of 8 over 5, and it'll stop at f of 9 over 5. And again, you can write that in, or I'm just going to start typing it onto my calculator here. So I want to pull up this last line here, actually. And I've got the 1/5. I've got the 5 over 6, 7 over 5 over 7, 5 over 8, 5 over 9. I don't want 1/2. I'm replacing f of 2 with f of 1. So I'm just going to type in a 1 right there. That gives me 0.746. Okay, and that's my bounded region then. So 0.646 is less than the actual value from integral from 1 to 2 of 1 over x dx, which is less than 0.746. For this one, remember that the square root of 1 minus x squared is a half circle. We're only looking at a quarter of it, though. It's from 0 to a quarter of a circle. It's from 0 to 1. So the lower, in this case, the lower will be right. So the integral from 0 to 1 of the square root of 1 minus x squared dx is about equal to, let's see, what's delta x? It's 1 minus 0 over 1, 2, 3, 4, 5 over 5 subintervals. So it's 1/5. If it helps you to keep track of it, write out 1/5, 2 over 5, 3 over 5, 4 over 5. Starting on the right, so the first endpoint is here. So f of 1/5 plus f of 2 over 5 plus f of 3 over 5 plus f of 4 over 5 plus f of 5 over 5, or just 1. Here's one where I definitely don't want to type all of this every time on my home screen, so I'm going to go into y equals, make it the square root of 1 minus x squared, and then on my calculator screen, I'm going to type in my function notation. So 1/5 times y1 of 1/5 plus y1 of 2 over 5 plus y1 of 3 over 5 plus y1 of 4 over 5 plus y1 of 1. So for the lower, I get 0.659. Okay, so let's see what this one is now. For the upper, the integral from 0 to 1 of the square root of 1 minus x squared dx can be approximated by 1/5. So now we're going to be on the left, so we're starting at 0. Then we have all of these values except for f of 1. So we end at f of 4/5. And remember, you have this typed into your calculator. You just need to trade out f of 1 with f of 0. So, and don't assume that that's 0. So go back up and grab this line. Change f of 1 to f of 0. It's not equal to 0. It's equal to 1. So you don't want to leave it out entirely. And that's 0.859. So we're saying that somewhere between 0.659 and 0.859 lies our actual area underneath this curve. Okay, here's another little round of practice with these eyes. Now, the reason I'm having you practice this with the eyes is because these are the limit definitions of integrals, of definite integrals. So it's worth practicing, but you do not have to have the eye sums memorized for the AP test. So again, why are we doing it? Because it's good practice if you have to take this in college on being able to do something abstract. So, all right, so here's what we have to work with. Find this limit of this value. So keep your limit notation. When we do this with integrals, the first thing we do is try to get rid of the summation. So get rid of the summation. There's a constant out in front, 24 over n squared. And then we have a formula for what is the sum from 1 to n of I. So there's a little pattern for that. I'm going to flip back to our notes. It's right here. Apparently it's n times n plus 1 over 2. So I'm going to say, instead of the sum of I, I'm going to say that's going to add up to n times n plus 1 all over 2. And now it's just a limit at infinity. So this is 24n squared plus some other terms over 2n squared. So that's a limit of 12. Same thing here. I like to kind of simplify first. Like, what is this expression? This is, I've got the limit as n approaches infinity of what's the constant I have? I have 4 over n squared. And then again, it's just times the sum from 1 to n of I. So times n plus 1 over 2. You have 4n squared on the top. You have 2n squared on the bottom. So that limit is 2. For this one, I need to do a little bit of work before I get started. So I'm going to do this off to the side. What is I minus 1 squared? It's I squared minus 2i plus 1. Multiply that by 1 over n cubed. So I have the limit as n approaches infinity of, I haven't gotten rid of the sum yet. I'm just writing out what I actually have. So, all right, what do we have in here? We have 1 over n to the third I squared minus 2 over n to the third I plus 1 over n to the third. I write it out like this so that I'm still going to be using the formula for what's the sum of I squared, what's the sum of I, what's the sum of a constant. But I like having the coefficients already out in front so that I don't miss anything. So the summation symbol is gone because I'm using this rule. I've got 1 over n to the third. And then let's look back at what is the sum of an I squared. So right here, the sum from I equals 1 to n of I squared is this expression. N times n plus 1 times 2n plus 1 all over 6. N times n plus 1 times 2n plus 1 all over 6. And then this middle term is minus 2 over n cubed. It gets multiplied by what was the sum of I, that was back here, n times n plus 1 all over 2. And then don't forget about the constant, plus 1 over n cubed. Our rule for a constant, this one's easy to overlook. When you have a constant, it's n times that constant. So back here, I have a constant, it gets multiplied by n. Now we have enough to do these limits. So what is this one? This is 2n to the third plus other stuff over 6n to the third. So that's 1/3. These 2's are going to cancel out. So you're going to get n squared over n to the third. So that's minus 0. And this is 1 over n squared, bottom heavy again, so plus 0. So this limit is equal to 1/3. The limit of this sum is equal to 1/3. And that leads us into these problems here. So use the limit process to find the area of the region between the graph of the function and the x-axis over the interval. Sketch the region. So start with the sketch. Got to get my pen working again. All right, so start with the sketch. We're on 0 to 1. So if you plug in 0, you get 5. If you plug in 1, you get 1. Something like that. So here's the graph. We're trying to approximate the area in here like this. To do that, you start with finding a formula for delta x. Delta x is the end of the interval minus the beginning of the interval divided by n subintervals. So it's 1 over n. And then find f of xi. So remember, instead of saying we're going to start on the left or the right, we say we're going to start anywhere in this interval, somewhere set at I, and then we're going to let the rectangles be so small that their width approaches 0, and that makes the number of rectangles approach infinity. So we need an expression for this x sub I. So the original function is -4 times x plus 5. What are we going to sub in here? We always sub in the same expression. It's the beginning of the interval 0 plus any number of delta x times I. I could be anywhere between 0 and 1, but we're going to multiply it by a width of delta x. So that just means, okay, I don't know, start at the 3rd triangle or the 4th triangle or the 17th triangle or whatever. And then replace delta x with your value for it. So -4 times, this 0 is unnecessary, 1 over n times I becomes I over n plus 5. And I might write that as like -4 over n times I plus 5. Okay, so these start off the same way. What we're doing is finding the exact area from 0 to 1 of -4x plus 5 dx. It's not about equal to anymore. It is equal to the limits as n approaches infinity of the sum from I equals 1 to n. You have to have all of this information, by the way. Don't leave off the notation. This is another homework where you would have to write it exactly as it is to get it correct on a quiz or a test. Okay, and then of what? It's delta x times f of x sub I. I like to write this out for myself before I sub stuff in because it gives me a starting point. This is like my definition to go off of. The next thing I'm going to do is just sub in expressions for those two things. So yes, it is tedious to write all of this over and over, but here we are. So delta x is 1 over n, and it needs to get multiplied by, what was my final thing here? -4 over n times I plus 5. Next thing we're going to do is drop the summation symbol because we're actually going to find the sum. Now what do I have here? I have -4 over n squared. What was the sum from 1 to n of I? It was n times n plus 1 all over 2. All right, and then the next term is plus 5 over n. I've distributed this through. The sum of a constant is the constant times n. Now I can take this limit. -4n squared over 2n squared is -2. Plus 5n over n is plus 5. So the integral from 0 to 1 of -4x plus 5 is equal to 3. Does this seem reasonable? I got a positive answer. That's a good sign because the area is positive in my picture. And if I were to do the area of like this whole rectangle here, it would be an area of 5. So 3 seems reasonable if you take a little chunk out of it. You can kind of check your work on these a little bit, just to at least see if they seem reasonable. Oops, I forgot this. dx. Sorry. All right, let's graph the next one. So 4 minus x squared between -2 and 2. So here's -2. Here's +2. 4 minus x squared hits 0 at those points. When I plug in 0, I get 4. I know that this looks like a little parabola. And we're talking about this area in here. First, find a delta x. It's the end of the interval minus the beginning divided by n subintervals. That's +4 over n. What is the expression for f of x sub I? So the original function is 4 minus something squared. We always start at the beginning of the interval, and we say we're going to add delta x times I, which just means the first triangle can start at I, which is any value in between -2 and 2. And to get there, I would add a certain number of delta x's. All right, so let's work on this a bit. I always do this algebra off to the side because I don't want to have to keep rewriting my limit and summation notation. So when I square this binomial, I get 4 minus 4. Oh, sorry. I don't want to square it yet. I haven't replaced this stuff yet. Try that again. So 4 minus negative 2 plus 4 over ni squared. Okay, so when I square this out, I get negative 2 times negative 2 is 4. Negative 2 times 4 over n is negative 8 over n. You're going to double that to negative 16 over n times I. That's just the rules for squaring a binomial if you use the shortcuts. And then the last term is going to be this squared. So that's 16 over n squared I squared. Now distribute this negative through. The 4's cancel. I get positive 16 over n times I minus 16 over n squared times I squared. Now set up the integral. The integral from negative 2 to 2 of 4 minus x squared dx is equal to the limit as n approaches infinity of the sum from I equals 1 to n of delta x, maybe I'll write this up here, delta x times f of x sub I. Let's sub in what we know. Delta x is 4 over n, and f of x is what I just simplified down here, 16 over n times I minus 16 over n squared times I squared. The limit as n approaches infinity of, let's get rid of our summation. So what constant do we have here? We have 64 over n squared. What's the sum from 1 to n of I? N times n plus 1 over 2 minus 4 times 16 is 64 over n times n squared, n to the third. What was the rule for I squared? Good question. N times n plus 1 times 2n plus 1. N times n plus 1 times 2n plus 1 over 6. And now we take the limit. We have 64n squared over 2n squared. That's 32. We have, you could reduce this 2 over 6, 1 over 3. So either say 128 over 6 or reduce that to 64 over 3. So minus 64 over 3. And, I could get, let's see, what's 32 times 3? It's 96 over 3 minus 64 over 3. And that is 32 over 3. So I'm calling it f of x dx. So that's the actual area that we get. Okay, lots of long problems in this one, right? All right, so let's see. Approximation. Use these two, or in these two problems, determine which value best approximates the area of the region between the x-axis and the graph. So sketch the graph to start. This is kind of what I did when I said I can see if my answer makes sense on an earlier problem. So let's graph this from 0 to 2. When you plug in 0, you get 4. When you plug in 2, you get 0. I know this is a half of a parabola that opens down. We're talking about this area here. Right away, I can see that the area is positive, so I'm going to rule out the negative area choice they gave me. And then how do I know whether it's 6, 10, 3, or 8? So use Riemann sums, but use like extreme versions. What if we use one rectangle? If I use one rectangle, the estimate is 8, right? So 10's out and 8's out. I know it's not 10 or 8. So now it's like, okay, is it 3 or 6? My picture looks like it's probably 6. But here's another way to check this. Cut it in half. Half of the area, half of this extreme area is 1 times 4. And I know it's bigger than that. So it's not going to be 3 because 3 is smaller than what I think roughly half of that area is. So it's got to be 6. Okay, and then kind of the same idea, for the next one. So first graph it. Now a sine graph is sort of like, that's a little harder to do, but plug in 0, you get sine of 0 is 0. Plug in 4. When you plug in 4, you get sine of pi. That's also 0. What's halfway in between 0 and 4? That's 2. So what's the sine of 2 pi over 4? That's just the sine of pi over 2. Sine of pi over 2 is 1. So I did that to make sure it's this part of the sine curve, not the one that dips down below. So we have this portion of the sine curve here. Again, I know it's a positive area, so I'm going to rule out the negative. And I'm going to do the same thing. What is the maximum area? Well, if I just did one big rectangle to encompass this, I could say, okay, 4 times 1, max area of 4. So that drops out 8 and 6. Now, is it going to be 3 or is it going to be 1? I'm going to guess 3, but I can do the same trick where I say, okay, well, half of it has an overestimate of 3. 2 times 1 is, no, of 2, sorry. So half of the area is 2, which is definitely bigger than 1, so I can rule that out. All right, what about 85? This is our last question. Consider this region bounded by the graphs 8x over x plus 1, x equals 0, x equals 4, and y equals 0 as shown in the picture. I'm not going to redraw the picture, but the first part says find the lower sum. Okay? The lower sum using 4 rectangles. 1, 2, 3, 4. The lower sum would be the left sum because this is an increasing function. So the integral from 0 to 4 of 8x over x plus 1 dx is about equal to, I can see there's a width of 1, and I'm just going to say f of 0 plus f of 1 plus f of 2 plus f of 3. Now, I think on my answer key that I posted, I probably subbed these numbers in, but I'm going to use my calculator anyway. I don't have to show the numbers subbed in for my AP test. So I'm going to, again, type in what this function was. It was 8x over x plus 1. Or a reminder that you can alpha y equals and get the little fraction thing here, which is nice. Okay, either way, whatever. So then I want to calculate all of this. So I don't need the 1 times, but I just am going to type in y1 of 0, or that's 0, so I could probably skip that, plus y1 of 1, plus y1 of 2, plus y1 of 3. And that comes out to 46 over 3. If I want that to be not a fraction, I can say make it a decimal. 15 and a third. Okay, so 46 over 3, 15 and a third, doesn't matter. We do round to 3 places for our AP test. All right, and then part B is same idea. 4 rectangles, find the upper sum. So the only thing that's going to change for the upper is where I start and where I end. Width of each rectangle is still 1. Instead of starting at 0, I start at 1. And instead of ending at f of 3, I end at f of 4. And the great thing about having this typed in already is I can go up here and I can just slightly adjust my answer. So instead of y of 0, I have y of 4. What is this as a decimal? 21.733. I like getting the decimal version for those because my brain is not going to easily compare the fractions when they're in those forms. But yeah, so far we have a lower and an upper. Okay, and then part C, this is the first time we've had to do this. Find the midpoints. So the midpoints are going to be like 1/2, 1.5, so 3 halves, 5 halves, 7 halves. So those triangles are going to be like this. Kind of hard to sketch that in. Okay, so part C, the integral from 0 to 4 of 8x over x plus 1 dx is about equal to 1 times f of 1/2 plus f of 3 halves plus f of 5 halves plus f of 7 halves. And I hop over to my calculator here. I'm just going to retype it because I have all those fractions, so easier than writing over things in my mind. Okay, 1357 halves. I would like that to be a decimal. It's doing fractions, by the way, because I entered in my y equals as a fraction, so that's the one thing. So 19.403 does fall between these two values. Every year I get students that say, where are these numbers going, by the way? I get students that say, oh, okay. Isn't the midpoint just going to be the average of these two? I don't think that's necessarily true. We can do a quick check here. If I just find the mean between these two numbers, is that, let's see, 15.333 plus 21.7333, 733, divided by 2, 18.533. That's not what I just got, right? So I think the reason it's not just a perfect average is because you're not, when you do the left and the right sums, it's not that you have the exact same area left out as overcompensated for. Like, it's hard to see it here, but here's the chunk I leave out. When I overcompensate in that rectangle, it looks to me like a smaller chunk that's overcompensated. So I don't think it's going to be a straight average. It might be sometimes if that relationship is true, but I don't think that would be the case for most functions that we look at. All right, that was a long homework assignment, but you should be very well versed now in upper and lower sums. Come see me if you want even more practice.